welcome to the fourth class of this week. In the first three classes, what we discuss is when a material is subjected to certain kind of threat, then as a response to that threat, stress generates in the material, and then also the material undergoes deformation, right. So, in the first 3 weeks, we try to understand what is the definition of stress, how the stress is represented, and what are the different properties of stress components. Now, we will do the similar exercise for strain today. So, today's topic is concept of strain. You see, in any engineering analysis, one of the very important steps that we do at the beginning of any engineering analysis is idealization. We always perform analysis on the idealized system, not on the actual system. For instance, if you recall your mechanics course or first year or structural analysis course, you studied how to analyze truss, you studied how to analyze beams, frames, and so on. So, whenever we call in nature there is nothing like truss, there is nothing like beam, plates, and so on. But when we say that something is truss, it means that we have idealized that particular structure as truss. Similarly, when we say that something is beam, means we have idealized the structure as beams. Now, every idealization is based on certain assumptions. Now, these assumptions are very important because these assumptions are essentially the limitations of any theory. Wherever those assumptions are not applicable, we cannot apply that theory. So, it is whenever we do study any formulation, whenever we do learn any theorem, it is very important for us to understand what are the assumptions which constitute the basis of that formulation. Okay, you see, suppose one thing we have understood that deformation is a response of a material body of an object to the external threat. Now, for instance, suppose we have this is suppose a plate. Okay. Now, if I apply some torque here at this point and also at this point, then it undergoes deformation like this, right. Now, if I keep on increasing the torque or the moment here, not the torque, if we keep on increasing the moment, the deformation increases, and you see we may have some point of time we may have a deformation like this. Now, why I am showing this example, because you see when the deformation is like this was a very small deformation, right. But if I keep on increasing the load, the deformation increases, then deformation is so large or the deformation is such that it cannot be coined as, it cannot be treated as small. Now, all the theories, all the definition of stresses, definition of strain that we are going to do today, everything, the relation between stress and strain that we will be studying in the subsequent weeks, everything that we have been discussed and everything that we will continue to discuss most of the time of this course, one of the important assumption is the deformation is very small. Okay. So, the deformation is very small. So, this is an idealization. We only can apply all this theory, all this definition of stresses, the strain and the relation only to those problems where the small deformation is a valid assumption. But there are many cases where the small deformation cannot be is not a valid assumption. You have to deal with large deformation, finite deformation, and towards the end of this course, we will spend 1 week on how to deal with those finite deformation. But till then, everything that we discuss with an assumption, a small deformation. Now, what is the consequence of this small deformation? For instance, okay, so suppose a material body like this, and it is undeformed configuration, and this is the deformed configuration. If you see the cells here, the small rectangle, and this is in deformed configuration, these become this. Okay. Now, before that, suppose we have a function, y is equal to say a plus bx square, bx plus cx square plus dx cube and so on. Suppose a function, a nonlinear function, is a polynomial. This is how a and x are related to each other. A, b, c, d are the constants. Now, if x is very small, if x is very small, okay, then what happens? Then all these the contribution of these terms are very small. When x is very small, x is essentially tends to 0, which is small, x is equal to epsilon, which is very small number. Then the contribution of all these terms, because they are the higher order term, the contribution of all these terms becomes 0. So, in that case, your y can be written as a plus bx. Okay. So, then in that case, y and x can be idealized as, if x is very small, can be idealized as, the relation between y and x can be idealized as linear, right. Now, y and x, depending on the context, you substitute the parameter y or x. Suppose if x is stress and y is strain, then the relation between stress and strain is linear. If the x is displacement and y is strain, the relation between strain and displacement is linear, and that linearity that linearity is valid assumption as long as this x is very small, and that is the thing that we have been discussing and we will continue to discuss. The deformation is very small. Okay. Now, so if it is undeformed configuration, it is deformed configuration. Okay. What we are going to do today is, if a material, if an object undergoes deformation, then the strain is essentially the measure of that deformation. Then how to define strain? The same way we define stress, we had also will define how to define strain, and what are the and how to represent strain in different way, different form, and what are the properties of the strain tensor, like the properties of stress tensor that we studied in previous lectures. Okay. Now, before that, let us see how a material in a three-dimensional space, if we have an object in three-dimensional space, what are the possible mode that object can deform. Here you all might have you all know, I believe, the term called degrees of freedom. It is the freedom of an object that that can in three-dimensional space, the number of freedoms that an object can, the different way that an object in a three-dimensional space can deform. So, in three-dimensional space, any object can have 6 degrees of freedom. When I say any object, without any constraint, okay, any free object can have at most 6 degrees of freedom. And then and what are those 6 degrees of freedom? 3 translation in 3 direction, and then 3 rotations about 3 axes. Now, if we project them onto the 2-dimensional space, then on 2 dimension we have only 3 degrees of freedom, 2 translation in the direction of 2 axes, and then 1 rotation, the in-plane rotation about the normal axis. So, this is the 3 degrees of freedom that an object can have in 2 dimension. What we do, we will try to understand or define stress in 2 dimension, and the same thing can be extended to 3 dimension. Okay. So, now, okay. So, you see, so this is the this is the undeformed configuration of a beam, not a beam, it is an undeformed configuration of any object, and the corresponding deformed configuration is this. Okay. Now, if we take any rectangular, any cell here, this cell maps to this cell actually goes here. Okay. Or if you take any circular small domain here, this is transferred to this like this. Okay. Now, this transformation, this map from undeformed configuration to deformed configuration, suppose this map is represented by phi. Okay. We will not discuss what is this phi and how to construct this phi, but this map, this projection must satisfy certain properties. Okay. Now, in a very general way, a general continuum, when we define strain, ideally we should take care of this map, and then From that we define what are the different components of strain and what are the different measure of strain. Now, but here we won't do that. Here what we do is we take a small element, for instance we take a small element, this element, and which is in deformed configuration become like this. We will take a small element the same way we took a very small element, infinitesimal element in the case of stress when we define stress. Similar way we take a small element and then see what are the possible deformation mode that small element can have, and then try to formulate the strain, try to define strain and try to calculate strain with geometry of that small element. Okay. Now, but we will come to this point, we will define this map. There is a term called deformation gradient, deformation gradient. We'll come to this point, we'll define this deformation gradient, which is essentially gives this projection from one undeformed space to deformed space, but we'll come to this point probably in the lecture 11 when we talk about nonlinear elasticity. Okay. Now, take this is a possible deformation mode, a typical deformation mode that as a two-dimensional object can have. All the deformation are in plane deformation. But remember here the rigid body deformation, for instance, is if rigid body deformation is if an object is like this, the object rotates as it is and the object translates as it is. This is, so from this point the object comes here, from this point object comes here. This is called rigid translation. This translation do not change, do not create any strain in the body. Okay. It does not cause any change in shape or change in volume, no deformation in the body, only the translation. Similarly, this object can come to this point, can translate in this direction and have and take a position like this, or this object can translate in any arbitrary direction and can take a position like this. These are called rigid body translation. Okay. This is rigid body translation. Similarly, this object can rotate as well. This object can rotate as well without causing any deformation, rotate about this, and this is called rigid body rotation. So, rigid body rotation. So, when in this figure, when I showed these three deformation mode, they are not rigid body translation and rotation. In all the deformation causes strain in the material. Okay. Now, if we have two direction, x and y direction, one possible is the extension in x direction or the contraction in x direction, either increase the length or decrease the length. Similarly, in y direction you can have a change in length in y direction, either increase or decrease, and these are called normal. The movement is in normal direction, in the x direction. This movement is in x direction, this movement is in y direction. Now, the another movement is the shear movement. We will come to this point, what is shear. So, these are the three possible deformation mode that a two-dimensional object can have, and all the deformation mode cause strain in this object. Now, let us consider. So, whenever we, if we go back to the previous, whenever we have this object, this point, this goes here. So, it is just not only extension in x direction or y direction or only shear. It has all different combinations of this typical deformation mode that act together, and that all act together and cause deformation in an object. Okay. Now, take a very general case. Consider this one is an undeformed configuration. The red rectangle is an undeformed configuration, and this rectangle moves here. This is deformed configuration. This is undeformed, and this is deformed configuration. Okay. Now, say A, B, C, D are the points and corresponding points are A dash, B dash, C dash, C dash. These of these infinitesimal small area. So, the area the length is dx and dy. Okay. Now, so let us first try to understand all these different this u v written here. Now, this point, suppose x direction, this in x direction we call u is displacement in x direction and v is displacement in y direction, and both are function of x and y. Okay. So, suppose this point, the point A moves here, and suppose this distance is u of x, u x y. Okay. And similarly, the point B moves here, and what is the coordinate? What was the initial initial coordinate of point B, initial location of point B? This is dx. The point B was dx, right? So, this is called, this is u of x plus dx and y. Okay. So, similarly, so this point is point in y direction, the displacement is v. So, point A moves to A dash, so corresponding y displacement is v, and then corresponding y displacement of C moves to C dash. These become this distance was dx. So, this become, so this is v of x y, and this distance was dx. So, and this, therefore, this becomes v of x, this distance was dy, then this becomes v of x and y plus dy. Okay. Now, so we will come to this point. Now, then the change in angle, this angle initially was 90 degree. Okay. 90 degree, and this is the change in angle. The change in angle is alpha, and then here it is beta. So, total change in angle is alpha plus beta. Now, let us fix our sign convention. The sign convention is tension is if the change in length, elongation is positive, means if it is in this direction, this elongation is positive, and then this is negative, change in length, decrease in length is negative, and then for angle, what happens if it is initially these two points are orthogonal to each other, this is 90 degree. Now this angle is less than 90 degree. If the angle decreases between two line AB and AC here, two initially orthogonal line, the angle decreases, this is considered as positive. If the angle increases, that is considered as negative. So, change in angle is alpha beta. Okay. Now, we have three, as just in the previous slide we discussed, there are three deformation, the typical deformation mode: translation, elongation in x direction, elongation in y direction, and then shear. Now, elongation in x direction means that initially the length is dx. So, there will be change in length in x direction. Initially the length was dy in y direction. The elongation in y direction means the change in length in y direction will be, there will be change in length in y direction, which causes strain in y direction, and then shear is this, there will be change in length, change in angle, this angle, which is this angle. So, the alpha and beta, they are the measure of shear strain. Okay. So, let us first understand what is the, let us first find out what is the strain in x direction, means what is the change in length in x direction, and then corresponding strain in x direction. Okay. So, so this is the, we can, yes, that is better. Okay. Now, you see, suppose this u that u at x plus dx and y. Okay. If we expand it with in Taylor series, then we have x y plus del u del x into dx, and then plus half of del 2u del x2 dx square, and then plus so on. Okay. Then we have all other higher order term. Now, just now it was the beginning of this lecture, we discussed that this is a small area, infinitesimal area, dx is an infinitesimal area. So, all these higher order term will go away. Okay. So, essentially we are left with u of x plus dx y. This essentially become u of x y plus del u del x into dx. Okay. Now, this will vanish. This is so small that we can neglect. This we can neglect, we can make it 0. Okay. If this is this, then u of x plus dx y minus u of x y, that is equal to del u del x into dx. Now, look at this, and what is this? What is this expression? This expression is essentially your change in length in x direction, right? Change in length in x direction. Now, similarly, if we do the similar exercise for say y, so if it is we can write say v of x y plus dy. Following the same exercise, it can be written as v of x y plus del v del y into dy, and this gives us v of x y plus dy minus v of x y, that is equal to del v del y into dy, right. Okay. Now, so let us find out what is, so let us find out what is this distance and then what is this distance. Okay. We are not, we have not yet defined what are the strain in different direction. What we are trying to understand it, if an object, a rectangular object moves in this way, deforms in this way, then just from the geometry we are trying to understand what are the different dimensions. Okay. What are the different okay. Now, let us find out this length. How do we get this length? Now, this b was this b moves from b was there, and this b moves from this. So, this distance, this total distance is, if I write it, this is, if I this distance total is, that is v of x plus dx y, right. So, this was v of x y, and this b was at a distance of delta x dx, and therefore, this becomes v of x plus dx into x plus dx of y. And similarly, the point C, if the point C is this, so this distance become u of x y plus dy. Okay, because the point C was at a distance dy. So, when it moves, so point C dash, the corresponding coordinate of point C dash will be x y plus dy. Now, similarly, if we express v x plus dx in Taylor series like this and u x plus x of y plus dy in Taylor series like this, what we get is, we get this v of the same thing, we get v of x plus dx y minus v of x y is equal to del v del x into dx, right. And then similarly, we get u of x y plus dy minus u of x y, that is equal to del u del y into dy. Now, we are almost, so these two are important. So, what it tells you that that the movement of point B dash will be this, which is equal to this minus this, which is del v del x into dx, which is del v del x dx. And similarly, this tells you the movement of point C in x direction, which is this minus this del u del y into dy, which is del u del y into dy. Okay. So, these four are important. Now, let us once we have done this, now let us define what is the strain in x direction. Now, strain in x direction will be what? Strain in x direction, if you recall in your we discussed strain is essentially what? Change is essentially the change in length divided by the original length. Now, if we are measuring change in length in x direction with respect to the original length in x direction, that gives us strain in x direction, which is written as epsilon say x, very similar to sigma xx. Now, that will be, so initially the length was AB, and that AB becomes A dash B dash. So, the change in length will be A dash B dash minus AB, and divided by AB is the original length. Okay. Now, you recall just now we wrote that okay, then AB was what? AB was A dash. Let us find out what is A dash B dash. A dash B dash. Just now in the previous slide, if you recall, the change in length in A dash B dash was del u del x into dx. Okay. Then, so A dash B dash will be initial length plus change in length del u del x into, that is A dash B dash. Okay. Now, then this is okay. Now, and then what is initially AB? AB was initially AB was dx, and then what we have finally epsilon xx is equal to this, from this we have del u del x. Okay. Okay. Now, in some places you will find that A dash B dash is obtained as okay, I can write it that as well. In some places you will see that A dash B dash is obtained as this square plus this square, means and then ignore the higher order term, essentially we will get the same result. Okay. So, now once we have epsilon xx's, so similarly we can define epsilon yy. Epsilon yy, if we do the same thing, like in this case A dash C dash minus AC divided by AC, and substitute what is the A dash change in length in AC. From this we get the strain in y direction, and that becomes epsilon yy become del v del y. Okay. Del v del y. Now, lastly, once we have epsilon x and epsilon yy, now shear strain is gamma xy, which is written as alpha plus beta, because total change in length is denoted by alpha and beta. Okay. Now, you look at this distance is del v del x into dx, and this distance is del u del y into dy. Assuming again a small length where A dash, the projection is almost similar, we have alpha is equal to del v del x. Del v del x means tan alpha is equal to alpha, that is what we are, and beta is equal to del u del y. So, this is the strain in gamma xy, the total shear strain. So, alpha will be this divided by dx, and beta will be this divided by dx, and tan alpha is equal to alpha, tan beta is equal to beta. That is how we have gamma xy. Now, this strain is called engineering strain. engineering strain. When we write in a tensor form, we just slightly modify this expression. We will come to that point shortly. Now, we can do the same exercise for 3 dimension as well. Now, for 2 dimension we have 3 strain component, one is epsilon x, epsilon y and gamma xy. Similarly, for 3 dimension we have 6 strain components, 3 normal component epsilon x, epsilon y, epsilon x x, epsilon y y and epsilon z z, normal strain in 3 direction, and then we have gamma xy, gamma yz and gamma zx are the shear strain on 3 different plane. So, total 6 strain component we have. Okay. Now, if we write that strain component, what we have is, now epsilon xs is this, epsilon xs is this, just now we define epsilon xs. Similarly, epsilon yy del v del y. In 3 dimension, following the same exercise, we can get epsilon zz. Now, we remember we wrote gamma xy is equal to del v del x plus del u del y, right. Now, that was engineering strain. When we write in a tensor form, epsilon xy is taken as gamma xy by 2. So, that is why this half comes. Okay. So, you be careful which strain you are dealing with. If it is engineering strain, then this is the expression. If it is tensorial strain, then this is the expression we have 1/2 here. Now, if we have 6 then strain component, and if we substitute that strain in this form, in a tensor form, then this become strain tensor, very similar to stress tensor. This is strain tensor. Now, not only that, all the exercise that we did for strain for stress tensor, for instance, the transformation of stress tensor, we can do the same exercise for strain tensor as well. Okay. Now, this is important. You see, now, so these are the all 6 strain component. Okay. Now, suppose we have a vector u, which is now please be careful about the symbol used, because this u here, what is UVW? UVWs are the displacement in 3 direction, x, y and z direction. Suppose that is represented by a vector u, which is written in bold letter. Okay. This is vector u. Okay. Now, if this is u, then in the first lecture, when you had first week, when you had the concept of the review of concept of tensor, and then you recall how to write the gradient of any vector. Okay. The gradient of any vector u can be written as this, when u, v and w are the components of this vector u. Okay. Now, look at this gradient and look at this corresponding expression for strain. What we can write is, now from this and from all these definition of strain, can we write that strain is equal to, as a tensor, is equal to gradient of u plus transpose of this, half of this. You see, the first component will be what? First component in this will be what? This plus transpose of this, half of this, means this plus again del u del x, and half of this become del u del x, which is epsilon xs. Similarly, if you substitute del u from this, and then we will get all the component of strain like this. Okay. So, this expression is very important. We will come to this expression again and again. Okay. Now, that was, so what we have discussed today is we define what are the different strain in a two dimensional object. But remember, the same exercise we can extend for higher dimension and get all the strain component. And while defining the strain, we we tried to define the strain through geometry with an assumption that it's a small deformation, so that higher order terms can be neglected. This term is very, you see all these expression, this gives you what? This gives you a relation between strain and displacement, or corresponding displacement. This relation is also called strain displacement relation. But look at this relation, these relations are linear relation. But as I said, these relations may not be linear always. There are some problem, or there are many problems where we have to take into account the nonlinearity in this relation, and then we will discuss that when we talk about nonlinear elasticity. Okay, that's what for the day. So, next class what we do is, next class we will just have a summary of concept of strain and strain. See you the next class. Thank you.